Thank you for kind introduction, and also thank you very much for inviting me to this fantastic space. And then usually the conference start with big discussion, and then I'm so afraid that the big main question. And then my name is Hisamoto Harima from Kobe University, but actually I retired 2 years ago at Kobe University. So I'm as a professor emeritus in Kobe University. And also, I'm a little bit working on the Famous Surface Museum and as a director, big director. And also that I'm working in the JPSJ as a Journal of the Physical Society of Japan as an editor-in-chief. That only 3 years, but this is just half of it. And before my talk, I should inform you about Professor Tadao Kasuya. I believe that most of you know him and his work. And he has passed away 2 months ago at his age of 98. And he got a cerebral infarction. And 4 weeks in hospital and 2 weeks in some place. Then he has passed away. And then this was a photo to take on the occasion for celebration of his 98th birthday this year. As his real birthday is the 1st of May, but usually, I forgot to say, he's my supervisor. And then we celebrated his birthday every year in Sendai. And then he went to the hospital the end of June. Then I suppose that this is the last photo of his life. And then we will have some memorial workshop in next March. Then I guess that some of you I've asked to write something about him later. Then I'm going to my talk. And then I'm working with the director of the Famous Surface Museum. Then my talk is about the Dwarf effect. This is the Lifshitz-Kodovich formula written in the main textbook. This is the kappa, the very beautiful oscillation. And then we have this is a spin factor. Spin factor means usually the Famous surface are generated by spin degrees of freedom. But today I'm talking about my talk will focus on the breaking inversion symmetry. In that case, the spin density is different, even in zero field, zero magnetic field. Then I'm very interested recently DHVF for uranium platinum 3, the famous superconductors. This is crystal structure and the calculated LDA calculation of the Fermi surface. And then as a biggest Fermi surface is observed by Noria Kimura, and also this typical topology is reproduced by the Fermi surface. But we should find many branches here, and many undistinguished signals, and they are assigned to the magnetic breakdown orbit by the Taylor-Hawk group. And they explained these as an orbit. This is the 5 orbitals, and they're equal separated. Very interesting. And they explained these 3 magnetic breakdown as orbit, like this one. This is as it goes through. Then the inner and outer, and then this is a 4 point. Then we have the 5 orbit. But it's very strange. Is the inner orbit is stronger than the largest one. And also the magnetic breakdown, and breakdown electron could tunnel from one band to another if the band gap between these 2 bands is sufficiently small. But usually the magnetic breakdown is observed at the Boolean zone boundary. This is not here. And these film surfaces are well separated. It's very strange. Then we look for the crystal structure of the uranium, superconducting uranium compound, the uranium platinum 3, and then the uranium platinum 3, the unit cell contains the 2 uranium, and then both uranium has lost the inversion symmetry. Then, but they are connected by inversion symmetry. Then the crystal structure has a central symmetric. And then we discussed later, as recently reported, this is the platinum 3 is not hexagonal but trigonal, but the situation is the same. And also the very famous uranium barium 13, the local inversion symmetry breaks at the uranium site, but they are connected by the inversion symmetry. And then they are as a non-symmetric, non-symmetric space group. There's no point fixed by any symmetry operation other than the translational symmetry operation. And then we look, this is a uranium platinum 3 crystal structure. It was said hexagonal crystal structure, and also the platinum point is fixed as an ideal point. Ideal point means that the platinum is the center of the 2 uranium site. But this as a local symmetry is a MM2. Then it is not a special point. Then it can be moved. And also this paper reported it is not a hexagonal but trigonal. And the platinum and the uranium is shifted up and down. And this is the hexagonal structure, band structure. And this is trigonal. And then here the split by lowering the symmetry. But the effect is not so big. So I discussed about this as a band structure. Then we look for the other uranium superconductor, uran, germanium, uran, cobalt, germanium, and also the local symmetry is broken, and then it's connected by a space inversion symmetry. Also the uranium, germanium too, and the famous uranium ditelluride. It's also the local inversion symmetry breaking, and then they are connected space inversion symmetry. It's a very unique structure in the uranium superconducting heavy fermion. And also in the uranium ditelluride, the fermi surface observed. This is the experimental result by Dayaoki, and this is a GGA plus U as calculation by using a U equals 2 electron volt. And this is my calculation, the thorium ditelluride, so no F difference material. Then it looks as almost no F electron in the near the Fermi level. And then the space inversion symmetry is broken on the uranium site in most of the uranium heavy fermion superconductors. And what happens when space inversion symmetry is broken? This is the first question. And also, LDA looks well predicting the Fermi surface in uranium platinum 3, but not in uranium ditelluride. Why? Because the uranium ditelluride as just LDA is a insulator. Then we need the U plus U for the uranium ditelluride, but it seems no U for the uranium platinum 3. It's why? It's very question. And how LDA is well in the uranium platinum 3. And this is again the DHVA, the angular dependence. And then the solid line is the calculated result and the dot experimental result. Then I give look the detail. The whole Fermi surface well, but we don't have in experiment we don't have such close to small Fermi surface. Then this part of the band should be lifted up. Then I suppose the plus U treatment necessary. But unfortunately, the experiment done before 2000, then we don't have the LD plus U the method at that time. But I tried sometimes LD plus U to reproduce the Fermi surface, but so far not successful. Then I'm going to the space inversion symmetry. As you know, the mirror is the inversion, but it is simple. Mirror plus the C2 rotation is the inversion because the XYZ is the mirror and XY change the minus x minus y because of C2, like this. Then it is simple. Then this is the axial vector and the polar vector as a mirror. Mirror change the vector like this, like this. But after that, if you rotate the vector the C2, and the axial vector does not change, and the polar vector is changed. This is as a result. And then the space inversion operator is a very special operator for the spin in solid state physics. Then I see that the log of the parity variation in solid means I say that the broken inversion symmetry is a parity violation. And this is the crystal structure. And then the time reversal, if you have the time reversal symmetry, as a light up equals the left down, the energy. But parity violation, the light up is not equal to the light down. This is because of the because the parity as a space inversion change the light up to the left up. Then if it's not a relation, this is not. Then the origin was lost of the space inversion symmetry. And this is parity, called a parity violation. And this is an example. This is a Ransome compound, metal. And then this is a crystal structure. And you can see the spin splitting like this. It's not big, but really it's split. And then what determines magnitude splitting? This is important is not only the spin-width coupling, but also the parity hybrid, because the on-site on-site hybridization of the odd and even as a wave function. Then, for example, this is the Fermi surface of this compound, and then they are as a spin split pair. You cannot see any change between them, but to plot the DH frequencies, there's a split here. And this is the experimental result, and this is the calculated result. So the band structure calculation reproduce very well this as a spin splitting, magnitude of the spin splitting. And then we move on to the YB4 antimonide 3. This is a anti-tritium 3 phosphorus 4 type crystal structure, and the space inversion is broken. And then this is the band structure. It is as a metal and non-magnetic. And then this is a J-core 7.5 band ytterbium. And then there are 6 folds. And then this is but 6 folds, but 3 pairs. But the experiment means that the 3 pairs and the 3 kinds of the Fermi surface. And at this time, the first time, the orbital theoretical prediction is 3 pairs. Of course, there are 3 splitted pairs in the Fermi surface. Then these are Fermi surface. It's very strange. It's only 6 holes, but the compensated metal. I mean, the even number of the electrons. And this is as angular dependence of the DHV as frequencies. And this is almost degenerated. There are 2. And this is an experimental result. And then this is fundamental. This is harmonic. But if you neglect the harmonics, there are many branches here, the 5 branches and 3 branches. Then what is the origin of these frequencies? Then this is the intensity of the DHVF frequency. And then the middle of the branch is the largest. And here the 2 branch. And here the 5 branch. And then of course the middle of the frequencies shows the very large intensities. Why? And then this is the quantum map of the Fermi surface. This is here is a 100 direction, the 4-fold symmetry. The 4-fold symmetry, there are the 4 crossing points. Then we'll have the 5 orbital branch. And this is the 110, a two-fold symmetry. Then we have a 3 branch. And here, 111 direction, it's we have the threefold symmetry, but not there is no crossing point. Then we have only the 2 branches. Then they are not magnetic plug, but we call it this orbital crossing through degenerate point. But this is through the degenerate point. But we can observe that not degenerate point, the tantalus disilicide. This is as a trace groups P622 or P6422. This is experimental the angular frequencies, and then this is the calculated one. And then there are the 2 closed Fermi surface. But here, some branches. Then this is the Fermi surface. There are also that almost the branches can be predicted by these calculated results. But here, there are 4 orbitals, right?
Sorry, quick question. Is the experiments, these are very low temperature
Very low
experiments,
temperature.
temperature?
Yeah, it's a DHVA. Yeah, it's a very low temperature.
Very low. So when the branch is extinguished, is that ellipsis? I mean, there's a thermal factor.
No.
Not because of that. Okay.
And then this is the intensity. Also the gamma branch and the gamma prime branch is the innermost and the outermost branch. And also that we have the 2 signals in between, because that these that we can be regarded these the orbitals. And then the ratio is 1:3:1, because if you have the gamma 1, there's a possibility around the 1 part here, or 1 part here, 1 part here. So that the ratio is 1:3:1. But it's very big as an intensity. And very interestingly, here, no degeneracy. It's not the symmetry point, or symmetry line. No degeneracy. Then there's a why these gamma 1, gamma 2 are larger than the gamma or gamma prime. They are unknown in detail, but maybe this is a spin-dependent effect. Because if we plot the spin texture, here the spin rotated or changed from the inner orbital to outer orbital. So this defines the possibility to the inner orbital to outer orbital. This is a special observation in non-symmetric compound. And going back to the UPT3, then I would say that these 3 orbitals are coming from the orbital crossing effect. But this is a central symmetric. But I showed that the all orbital crossing effect is a non-symmetric crystals. But why such as effect is observed in the platinum 3? But I would say that the platinum site is broken, inversion symmetry broken. Then 2 uranium is connected by a space inversion symmetry. Then I would say in the uranium platinum 3, the orbital consists of the mainly the one side spin, one side up spin, and the other side down spin. This is generated by the inversion symmetry. So I mean A plus B up and A plus B down. No, A up and B down. This is the inversion symmetry. Then in that case, the Cooper pair A plus A up and B up is favored, because due to the avoid the Coulomb interaction, big Coulomb interaction. And then in the uranium compound, so such a the parity violated effect is very evident, because this is a non-central symmetric platinum 5. This is this experiment done by Hisato, and then it's alpha and alpha prime the Fermi surface. And then this is a calculated result, but in between there are many EHV frequencies. This is the orbital crossing effect. And then, as I move on to the uranium ruthenium 2 silicon 2, it's also the famous as a superconductor in uranium. And then this is the angular dependence of the Shubnikov dwarf experiment from the Diaok's paper. And there's a very good angular dependence. Then this is a phase diagram of the uranium ruthenium 2 silicon 2. And the superconductor is realized here, that here is the hidden order phase. So we don't know the symmetry of the electronic state just above the superconductor. Then the unknown. Then but this hidden order state, the electronic symmetry should be locally invariant symmetry broken. And the two uranium sites are connected by invariant symmetry. That is we expect. We expect. Then I wrote another paper, hidden order of uranium compound. Then this is polar state of the symmetry of uranium and ruthenium-3. And we have subgroup without any distortion of crystals. We don't need any movement of the atoms. Just the same as the space group 139, but we have a lower electronic space group, only electronic. But there are 7 electronic states, such as subgroups, possible subgroup. And this is a ferro ordered state. This is not the case. And there are antiferro, it means electric multipole state. Then there are 5, and they corresponding to the rank 2 as a quadrupole and octapole, and rank 4 multipole and rank 5 multipole. This is the even and the odd. But in the experiment, NM1 experiment says as a ruthenium and silicon site, it keeps a four-fold symmetry in the hidden order state. Then also the one the possible space group is here. This is as a rank 5 electric dipole. This is the order parameter, x by z and x square minus y square. Then we'll have the similar as a heavy fermion superconductivity in the under the hidden order state. But this kind of the calculation, so the same atomic position, but lower symmetry of electronic. How we can recognize this one. And this is another crystal, cerium rhodium to arsenide 2. Also, this is a crystal structure P4 and MM. And also 2 possible subgroups without any change of the atomic position. And then this is an antiferro quadrupole state. And now we think this corresponds to this T0 in the cerium rhodium to arsenide 2. And my student 2 years ago, Numa, he is here, and he has a presentation of this conference. In his thesis, this is a lower space group assumed that the LDA, the antiferro quadrupole moment, is unstable. It's the LDA. But if you put the U equal 0.4 UV, so the antiferro quadrupole state is stable. So the crystal structure is the same, but we have the lower symmetry of electronic state. And the fermi surface is here degenerated, but its degeneracy is lifted in this antiferro quadrupole state. Then this is a summary of my talk. There are many fermion uranium superconductors. Local inversion symmetry broken, but the uranium sites are connected by the inversion symmetry. This is a very special, I think, the condition for the uranium as a heavy fermion conductor. And I don't say many about that, but 5F6T hybrids realized at non-centrosymmetric site. So if you have the inverted symmetry at the atomic site, the order parity and the even parity orbitals not hybridize. But many uranium compounds, it can be this effect. And the orbital crossing effect is realized even in the centrosymmetric uranium planet 3, as the space inversion is locally broken. Then we expect this as a pair, and this is better condition in the Coulomb energy for turbulent superconducting. I expect so. Thank you very much.